Any questions before we get started? So today we're going to finish up the aldol reaction, and then we're going to look at the Claisen reaction, which uses oxidation state 3 electrophiles resulting in beta carbonyl compounds. And there's a special feature of those that will look a little bit more in depth and how we can use those products to make other substituted acetones and substituted acetic acids. So we left off on this aldol reaction that gave two stereogenic centers, one at the alpha and one at the beta position. And so we have two stereo centers. 2 to the 2 is 4, so we end up with 4 total stereoisomers. So those are shown here for the aldol reaction of propanal. And so how many pairs of enantiomers are there? So there's 2 pairs. You can tell that in 2 different ways. One, if you look at these wedges and dashes. So the first pair is this first horizontal pair here. So if those wedges and dashes are exactly opposite, those are mirror images. And the other way you can tell is by looking at the CHE designations. So 2S, 3R, 2R, 3S. So that's one pair, and then the bottom row is the second pair. So again, the aldol reaction can produce, in theory, these 4 stereoisomers. And we'll see in a little bit about ways of controlling that, so we only get 1 out of that. So here we end up with 2. And then how many diastereomeric relationships are there? A little bit more. What? There's 4? So again, you can either look at the wedge dash nomenclature or the CHE nomenclature. So if we focus on this first one to the top left, that would be a diastereomeric relationship. So the beta carbon stays the same, the alpha carbons flips. Or this one here. Now the alpha carbon is staying the same and the beta carbon is flipping. And then we can do it from the other top right one. Those would be diastereomers. And then those would be diastereomers, so that would be 4. So as a review, remember that enantiomers have identical chemical and physical properties. The only thing that's different is the sign of the optical rotation that's measured in a polarimeter. Diastereomers have different chemical and physical properties. So for example, I don't know the exact values of these, but if these were both liquids, they would have different boiling points, diastereomers. Enantiomers would have the exact same boiling point. So due to the complexity, it can be hard figuring out those relationships. In the center of this slide, I have, for lack of a better way of describing this, the zigzag way of drawing things. And so in that convention, the longest carbon chain is always in the plane of the board. and then any substituents come out towards you or go away from you. So with that, you have carbons that are up and carbons that are down. And so their bonds have to be shown on whatever face they're on. So for example, in this third carbon, since it's down, you have to show its bonds pointing down. Say the second carbon, those bonds have to point up. So that's the convention of showing the stereochemistry along that. So organic chemists use that. That's important for polymer chemistry as well. There's a type of polymerization called Ziegler-Natta, where you're looking at the stereochemical relationship of those substituents. And so terms that are often used for these are syn or anti. The top two stereoisomers are called syn. In the relationship between the alpha and the beta substituents, they're on the same side, so syn. Then the bottom two, that pair of enantiomers, those are anti. So when you're looking at the substituents, one's towards you, one's away from you. So Ziegler-Natta looks at is there a repeating relationship among those substituents? Sort of everything syn, or is there anti, or is it some other random pattern? So when you look at it that way, that's probably the easiest to determine the R and S from the SIP rules. But historically, there's other terms that are used called erythro and threo, and those deal with the Fischer projection. So those names come from two sugars, erythros and threose, and they're dealing with looking at the relationship of substituents. But when you convert from zigzag to a Fischer, so notice that aldehyde carbon is the highest oxidized carbon too. In a Fischer projection, the highest oxidized carbon always goes at the top of the chain. And then the backbone, notice the backbone for zigzag. The backbone is always vertical in a Fischer projection. But what's misleading about it, if you put your eyeball like right here, and you're looking at that bond, it's easy to tell that the alpha carbon, that methyl group should go to the, which way are we facing here? So we're looking at it, the hydrogen's going back, so that methyl group goes to the left. See how these are syn here? But in the Fischer projection, notice that OH is on the other side. So what happens in a Fischer is that you're actually rotating around that carbon sigma bond. And so instead of having like a total zigzag, it kind of converts into something like this. So those bonds, those specific carbon-carbon bonds, the dihedral angle changes. So it essentially becomes 0. And then the carbon backbone is all in a vertical line now. So if you do that rotation, you can kind of see how those substituents end up on opposite sides of the Fischer projection. And the way that I remember this, this is called threo. That starts with T. The word different ends with T. And so the other one is erythros. So that starts with E, and the word same ends with E. So when they're on the same side, they're called erythro. So what's tricky in terms of the nomenclature, the words are conveying different things, whether it's zigzag or fissure. So when you rotate around that bond, the OH and the methyl end up on the same side. So that's erythro. And we'll learn about carbohydrate nomenclature in Module 5, where the origin of that is sort of used for in terms of an aldol. Yeah.
I'm assuming syn will always be trio and then anti will always be erythro.
I'll say 99% with an asterisk. So if I am wrong, I have some wiggle room. But yeah, it's just they're conveying the same molecule.
Right.
It's just a different tool of showing you the relationships. And again, when we get into Module 5, this is important for us because as we learn carbohydrate nomenclature, the zigzag representation of carbohydrates is a lot harder to interpret because you have more stereocenters. And so the fissure is a lot easier to learn. But in the literature, say in the 70s and 80s, the 1970s and 80s, erythro and threose were used more commonly, but now syn and anti are used more prevalent. So I have this song here, which I kind of like. So clowns to the left of me, jokers to the right. Here I am stuck in the middle with you. So the goal of any reaction is to produce one thing in 100% yield. You don't want to be producing enantiomers in a 1-to-1 yield. You don't want to be producing diastereomers in some other yield, because then it's a mixture of things you have to separate. And that takes time and money and effort. And it's better to design a reaction that produces one thing than spending your time separating those things. So diastereomers you can separate most likely by thin layer chromatography. So you've done that in lab. The compounds have different affinities for the mobile phase, the stationary phase, they separate. Enantiomers you cannot separate by TLC. That's just one spot that's going to move up the plate, and then there's no separation. So there's other things you would have to do for enantiomers. And if you're a pharmaceutical company trying to make a product, you don't want to add a step or a unit of work in there that costs money, because then that's a slower delivery of the pill to the pharmacy. Patients need it, it costs money, cost of drugs go up, et cetera, et cetera. So it's better to just design into the reaction, how can I produce one of the 4 possible stereoisomers? So the aldol reaction was studied quite a bit in the 60s and 70s and 80s for that reason. What do we know from just the basic principles that we can apply into this system to get one thing out? One of the easiest things to do is use an electrophile that's non-enolizable. So you don't have this competition that's producing more things. So the electrophile cannot enolize, it can only act as the sort of incoming or incipient beta carbon. Questions so far? So yeah, these are the non-enolizable aldehydes on the screen right now. So again, these will only act as electrophiles. There's no acidic alpha protons to deprotonate them. So they'll essentially end up as your beta carbon. So you have some other coupling partner, you form that enolate, then you react it with this in a cross-aldol reaction. However, one of the issues is with the pival aldehyde and benzaldehyde, for example, you're still ending up with a stereocenter at the beta carbon because it will have 4 different substituents. But you don't have to worry about any of these ending up at the alpha carbon because they cannot form enolates. So to dive a little bit deeper into this, and again, this is more of, for your knowledge, to show you how the thought process has evolved in controlling the number of stereoisomers. I mentioned David Evans in a prior lecture, and his doctoral advisor was Robert Ireland. And Ireland figured out how when you take one of these substrates with these alpha hydrogens, those hydrogens, even though they're bonded to the same carbon, are referred to as prochiral. Prochiral simply means if you do a test, you take one out, substitute it for some other group, you would end up with different compounds. If you did that substitution and you ended up with the exact same thing, those are not prochiral. So that just means is you abstract it, you substitute it, you're going to get a new compound that's different for each hydrogen. We kind of already know that because at the alpha carbon you can form an R or an S stereocenter. So that's what prochiral means. So Ireland figured out that using this base LDA, so that's lithium diisopropyl amide. That base is selective for one of those hydrogens. And the reason that is, they assemble in a 6-membered transition state. So if we count these atoms, so we'll start from lithium. So lithium plus, so 1, 2, 3, 4, 5, 6. And as I said way back in 255, nature prefers to do things in a 6-membered ring. So the 6 atoms is really crucial in nature. That lithium is plus. So it has an ionic attraction to the nitrogen because it's minus. It's also attracted to the lone pair of the carbonyl oxygen. And then when you look at the alpha carbon, you have the 2 hydrogens. Notice the displacement of the R group, whether it's that hydrogen or if we rotate, it's the other hydrogen. The hydrogen that gets abstracted is one that is axial in that chair transition state. That's because it better aligns with the pi star orbital of the carbonyl. So when that lone pair abstracts that, don't want to go that far. Of course, it's not letting me erase that. I'm going to draw it in blue. The lone pair abstracts the hydrogen. The electrons in that bond go into the pi star because that's the unoccupied orbital of the pi bond. And that's only achievable when the hydrogen's axial. So when you do that from the top transition state, what you end up is with the E enolate. The bottom transition state, when you rotate around that bond, it puts that R group next to this isopropyl group. And the red arrow is meant to mean steric hindrance, so that's unfavorable. If it does happen, that ends up with the Z enolate. So just by the choice of base, you're able to select out one enolate in preference for the other. So as I said, Evans worked in the Ireland lab and wanted to address this issue of basically accessing one of the aldol stereoisomers. And what he decided to do, if we focus on this X group right here, we're going to use a substrate where the carbonyl is oxidation state 3. So that means we only have one alpha carbon. And then those hydrogens are prochiral. So that X group, he made into a chiral auxiliary. And so that I'll highlight that in red. So X means that whole thing. So there's your oxidation state 3. And then what you notice about that group, this carbon right there is a stereogenic carbon. So I've highlighted it with an asterisk, that carbon right there. That's a set stereo center in the reaction. This whole thing comes from valine. We talked a little bit about alpha amino acids. So valine is readily available. What happens is valine gets reduced to an alcohol. And then the nitrogen and oxygen those two get cyclized with basically a carbon monoxide equivalent. So say phosgene. That carbon's at oxidation state 4. So you can take whatever you want to do the substitution of the alpha carbon or the aldol. So that acid chloride plus the amine, that gets you your sort of amide bond, and then you link that back with the OH through that, and that's called an auxiliary. So it has a set stereocenter. That stereocenter then dictates which of those hydrogens gets deprotonated, and then ultimately how that reacts with the aldehyde. So it's going to set that stereocenter and then the stereocenter of the new beta carbon. Absolutely. So you don't end up with a racemic mixture, you don't end up with diastereomers, you end up with one of the 4 possible stereoisomers. So all due really to the existence of that stereocenter, which comes from a naturally occurring amino acid. Sort of one of the complaints maybe with this. So here's your alpha carbon. For every reaction that you do, it has to incorporate that auxiliary, so it's stoichiometric. So that's a cost. Nowadays, people can run these reactions where that sort of auxiliary is its own catalyst, and you don't need it in a stoichiometric amount. So Evans studied this and did a lot of other things. He was not awarded a Nobel Prize for this, but probably should have been. It turns out one of his students, David McMillan, won the Nobel Prize in 2021, along with another chemist, Benjamin List, for taking a reaction like this and making it catalytic, where you no longer need the auxiliary. And again, I knew we can't learn everything at once, but see how that says L-valine? That refers to the Fisher projection. So if we draw that as a Fisher projection, so the highest oxidized carbon's on top, that's the stereocenter. When that group is to the left, it's called L. If a group is to the right, it's called D. So naturally occurring amino acids will have that Fisher projection. So that's one of the reasons why he used that one, because the natural one is cheaper to obtain. So we'll revisit this L and D nomenclature for amino acids and carbohydrates based on what is naturally occurring and then what is unnatural. So that's a portrait of David Evans, and what's shown here is the 4 possible stereoisomers and how you end up with only one. So in the gray box are the 2 main things. Here's your enolate. There's the auxiliary. So there's the stereocenter. In the Evans chemistry, based on the metal that's used, which is boron, that M, and these ligands, which are butyl groups. Let me see here. I spent an hour redoing this and I still have a mistake. This is showing the E-enolate, which is the top one. But the Evans chemistry favors the Z, which is down here. So if you flip these groups around, the Z-enolate is the favored one with that auxiliary. But that's how that looks. Forming the enolate, there's your metal, and then its ligands. So there's the aldehyde. Those things come together into a 6-membered ring. And anywhere you see a red ball, that's unfavorable. A green ball is favorable. So if we count 1, 2, 3, 4 atoms, 5, 6 atoms. So those can come together to form a transition state. And then here we see the Z-enolate, that's the favored one, stays the same. But then the orientation or the face of the aldehyde changes. So the green box, which is what the Evans aldol will produce, you have those groups in their most favorable steric interactions. So when they react, you get the syn aldol. And it's specifically that stereochemistry due to that auxiliary. So the other three, the ratios here in terms of like the major versus any minor are like greater than 500 to 1. So even if it is formed some other enantiomer or diastereomer, it's so low that it's almost beyond detection. Yep.
If you flip the stereocenter in the original molecule, what product would you get?
It would give this one, I believe, that enantiomer.
Okay.
So if you allow me to backtrack. So again, what's nice about this is, you know, for the most part, even though it is pretty advanced, it does rely on the basic fundamental knowledge you've learned in organic 1 and 2. You know, steric interactions, bond lengths, bond energies. How can you apply that stuff to control a reaction that produces one stereoisomer? And as I said, the chiral auxiliary, which is stoichiometric, is probably the main complaint. Because in your product, that's what that X group is. Ultimately, it has to be cleaved off. You can recycle it, but you still have to use it in a full molar equivalent. So David McMillan was a postdoctoral student in Evans' lab, and he was doing chemistry similar to this, but wanted to get away from that stoichiometric auxiliary. And so he investigated a reaction that had been known since the late 70s, where you can basically form an intermediate from a catalytic amount of a different amino acid. So this one's proline. So here's your alpha carbon. Proline's the only amino acid that has a ring. So it's a secondary amine. In the self-aldol reaction, taking propanal plus a catalytic amount of L-proline, that will generate the aldol product, so alpha, beta. Notice now it's the anti. Also notice the elements of proline are not incorporated into that product, right? So because it's a catalyst, it does something, it goes away and it gets recycled. And one of the reasons that McMillan and List won a Nobel Prize is because the way this happened more mimics what happens under physiological conditions in the body, how carbon-carbon bonds are formed in the body. So let's see if you remember some stuff. If you have a secondary amine plus an aldehyde, what do those two react together to form? There's an intermediate that's formed. So I'll give you a hint. You have H, H, and O. Huh? So that forms water. So it's a condensation product. A secondary amine plus an aldehyde lose water to form an enamine. So an enamine has a resonance form that sort of resembles an enolate. The nitrogen has a lone pair. Through resonance, we can put that lone pair on the alpha carbon. And so that then will react with a second equivalent of the aldehyde. And then ultimately, that iminium ion gets hydrolyzed by water. So the water releases the proline back into the catalytic cycle. And because that proline has a stereogenic carbon, it is relayed to the alpha and beta positions. So I've just drawn those with asterisks, but you're ending up with a very high yield of one of those diastereomers. So nowadays, that's called a catalytic asymmetric reaction. You don't have to have a stoichiometric amount of the auxiliary present. And the proline could be recovered or chuck it and start with a new batch. So that's,
Sorry, I had a question.
yeah.
So this is essentially, in this particular slide, it's a self-aldylation of the aldehyde, but with that as a catalyst producing a specific ester.
Yeah. So that's pretty much state of the art. Even more state of the art. People will take these substrates now. These enamines, you shine blue light on them. So blue light LEDs won a Nobel Prize a couple of years ago. It was found that blue light plus a photocatalyst, you can remove an electron out of this system and you get different modes of reactivity. So these Nobel Prizes, they push the envelope of mechanistic organic chemistry pretty far. Any questions before we move on? So you can do an aldol reaction within one molecule. This is called intramolecular. So intra means within. And if you look at it, you have a symmetric molecule, so it's a diketone. I'll put the numbers in for the chain. So within that molecule, one carbonyl is going to form the enolate. The other is going to be the electrophile. And since we're under conditions where we're using a weak base, we get this equilibrium setup that's ultimately going to form the more stable enolate. So that means we're going to either deprotonate from carbon 3 or carbon 6. So that generates the more substituted enolate that will then attack the carbonyl that's hanging out down the chain. We know that an aldol has to be a beta hydroxycarbonyl, right? So that's the substructure. But the two things are tethered together. So that means we have to form a ring. So we're going to get a ring that has a beta hydroxycarbonyl. We want to form the more stable enolate. So I'm going to deprotonate from C3. So if carbon 3 attacks carbon 7, what size ring are we going to form?
5.
So a 5-membered ring. So I'll write these numbers in blue. So the nucleophile starts at carbon 1, 2, 3, 4, 5. So we get a 5-membered ring. And now we have to put the substituents on. So carbon 5 has to become an alcohol. It also has a methyl group hanging off it. Carbon 1 has to have a ketone hanging off it. And then the last step, we just do the proton shuffle. So when you look at that product, you say there's alpha, there's beta. It's a beta hydroxycarbonyl. That has to come from an aldehyde or an aldol reaction, where we're making the alpha beta bond. And because we had both the enolate and the carbonyl in the same molecule, that's how we get the tether to make a ring. Any questions? So there it is with the product. And maybe what I can say is, always numbering your chain helps. And then when you're doing arrow pushing, always start with the nucleophilic site in terms of how you're counting numbers, that attacking the electrophilic site. So that's how we're able to determine it's a 5-membered ring. So 3 was our nucleophilic site, and then 7 was our electrophilic site.
And this will produce 4 different stereoisomers?
Yeah. So each of those ends up being a stereogenic center. Any questions? Okay, so now we're going to look at one oxidation state higher. We're going to be starting with esters. So we're at oxidation state 3. The conditions are similar. We're going to treat an ester with a base, and now we end up with a new product. The beta carbon is at oxidation state 2. So whenever you see that, you can tell that it came from a Claisen reaction. One thing I want to point out, of the ester, see that part I put in the box there? That's O-ethyl. You're going to use the same alcohol base. So notice the base that we're using is sodium ethoxide. So 2 equivalents of ethyl acetate form ethyl 3-oxobutanoate. If I put this oxidation state number there, 3, see how that's higher? 3 is higher than 2. So the parent has to be named as an ester, and then the carbonyl group is a substituent. When it's a substituent, notice its name, oxo. So oxo means carbonyl. So this is a self-Claisen. It's doing what we learned in the prior module. Remember nucleophilic acyl substitution? This group I put in the box, that is being substituted for all of this through an enolate reaction. The other thing I can say about this, notice that 1 alpha carbon, then the product actually has 2 types of alpha carbons. And then one of them is more special than the other. So that product leads into a new type of reactivity that we'll learn 2 more reactions from. So what happens? I want to do that. All right, this effing eraser here, this should just be a straight line. So this is an important then. So some of these arrows are in equilibrium, but we get to a point where it's not an equilibrium anymore. And that's why it's a one-way street after that. So we have sodium ethoxide, that's our base. That's going to form the enolate. That's the nucleophilic component. So that's an alpha carbon. Now it reacts with a second equivalent of ethyl acetate. So we reform the pi bond. The alpha carbon attacks that beta carbon. So that's a nucleophilic addition. Notice at that beta carbon, the oxidation state decreased. It went from 3 to 2. And now it has a good leaving group. So nucleophilic addition, now an elimination. We reform the pi bond, and then what leaves? Ethoxide. So that's fine because that's what we're running the reaction in. So that might look like the final product. But if you look at that alpha carbon, it's now sandwiched between two carbonyls. So those hydrogens have a pKa value of about 10 compared to the other ones, which are about 20. And so because we formed that sodium ethoxide, this is a thermodynamic deprotonation. That hydrogen is so acidic that once it forms, it gets deprotonated. And so that's the one-way arrow that gets it out of equilibrium. And so the reaction, once it gets there, it sort of sits like that in the enolate form until you adjust the pH. We'll just say pH less than 4, and all it does is reprotonate it.
Does it matter which oxygen gets enolated? Like which carbonyl becomes the enol?
I'll show you in a slide or two.
Okay.
So the deprotonation of that CH2 group. So this is a special type of CH2. Historically, it's called active methylene. So active methylene means you can use a pretty weak base to deprotonate it. You know, a base derived from an alcohol. So once it gets to that enolate, it'll sit. You can actually strip the solvent off those and isolate those enolates a normal enolate, if you did that, it would probably decompose somehow, but those things you can isolate them, store them as solids. Then in the reaction, all you do is just dribble in some acid, it reprotonates it, and you end up with the neutral product. But the key here is that step, those active methylene CH2s. If you think about everything we've learned, that's doing a deprotonation. If you didn't want to quench it with acid, you could use some other electrophile and substitute there. So you could take those H's and substitute them for other R groups. And those would be the final two reactions we'll learn today. So looking at I would say this is a beta keto ester. Looking at a beta keto ester, you should be able to determine what esters it's coming from. Because again, it goes through the nucleophilic acyl substitution. So how many different alpha carbons does this have? So this one again has 2, and the acidity of those is very different. So CH2 is, again, a methylene group. CH3 is methyl. So the methylene is more acidic. As Jason pointed out, which way does it enolize? It can enolize different ways, so that in alone makes it more acidic. It's more stabilized through resonance. So we'll say pKa of 10, and pKa of 20. So there's that product, the ethyl 3-oxobutanoate. When it does enolize, these are the possible enolates it can form. So the top case shows the enolate going into the ester. And then what you'll notice is the O sodium group sort of flipping. So you have these different geometries. The bottom two show the enolization occurring into the ketone. And then you have the Z versus E. So the fact that when you do enolize it, it can be stabilized through 4 different resonance hybrids. That helps explain the acidity of that as well. So I think we have the cross-Claisen coming up, but what I want to show is again, because those hydrogens are acidic, you can deprotonate them easy and then treat them with an electrophile to substitute them. And then from that, there's another little special thing that happens, and then you'll see about matching a pattern. The pattern really is the alpha and the beta carbons. Can you spot them? And then can you sort of think backwards where things come from? So for these, I'm not going to draw the mechanism, but this is a crossed Claisen. The same issue with the aldol. So I think if we draw the line this way, so on the left is your self products. So ethyl acetate plus ethyl propionate. Ethyl acetate can react with itself. or the ethyl propionate can react with itself. What you notice now is the beta carbon is sp2 hybridized. So from that fact, it can't produce as many stereoisomers as an aldol because the beta carbon is no longer a stereogenic center. But once you go out to a carbon chain 3 or longer, that's when you can get that stereo center at the alpha carbon. And then we see the cross products where one acts as the enolate, one's the electrophile, and then vice versa. And so that one also ends up being a stereo center. Questions? So say I can't cover it on, if I cover it on here, it isn't covered on there, so that would be dumb. But if I like cover all this up and I say, look at that, you should be able to tell me what it's coming from. So remember, you're always making this bond. So that would be your enolate, and then I cover that up. I add an O-ethyl group there, that's the electrophile. So you should be able to see those pairs, like whatever other junk's hanging off it. So when you look at, say, this one down here, in this module, we're always making an alpha-beta bond. When you look at the beta carbon, the oxidation state is telling you if it comes from alkylation, aldol, or Claisen. The alpha carbon always comes from the enolate. The beta carbon's the electrophile. So we get a 3-carbon ester here, and then this would be a 2-carbon ester where the original substituent is O-ethyl. So notice how they're both O-ethyl. You have to keep that matched because otherwise you'll get different products in a sense. Okay, so the same way that you control the aldol, you can control the Claisen using non-enolizable esters. So here's some examples of those. So notice the ester nomenclature, there's ethyl. So ethyl, 1-carbon aldehyde, ethyl formate. Here we have a non-enolizable ester, so ethyl pivalate, ethyl benzoate. And then what's unique about the last one? Diethyl carbonate. So 3 oxygens, what's the oxidation state of the carbon, central carbon? So that's 4, 3, 3, and 3. So notice again when you do a Claisen, there's a reduction, right? The beta carbon goes from 3 to 2. But if you start with diethyl carbonate, it's at 4. So it has to go from 4 to 3. So when you use diethyl carbonate, you're kind of switching the reactivity partners in a sense. I'll come back to that. I want to get to this point. This shows a reaction. It's a Claisen reaction, but you're starting with a ketone, and then you're going to use the diethyl carbonate as the electrophile. So notice in the product, that the ester part is coming from that. The beta carbon is coming from a ketone. So you can kind of flip the partners in that regard. So starting with cyclohexanone, generating the enolate with LDA. So there's your, what's going to become your beta carbon. That will attack the diethyl carbonate, a nucleophilic addition, substitution. That group I put in the box will leave, and now you've made an ester in a different way. So it's still a beta ketoester. I'm going to take a sneak. We do have about 8 minutes, but I'm getting a little gummy in the mouth from talking. So I think what we'll do is we'll stop here. And then now that we've made these beta ketoesters, what we're going to do is substitute off those alpha positions to make acetones. So a 3-carbon ketone, and then acetic acid derivatives, a 2-carbon acid derivative. Peak here.